bonding. Covalent bonding is not the loss or gain of electrons or transfer of an electron completely from one atom to another. It is actually the mutual sharing of electrons. By mutual, I mean equal sharing. If one atom shares an electron, the other one shares one too. They always share the equal number of electrons. And this is how a covalent bond is formed. So let's go with a few examples, understand the chapter topic by topic. So in any bond, the particles are held together by electrostatic attraction between positively or negatively charged some. However, in covalent bond, a pair of electrons is shared between two atoms. What holds atoms together is the strong electrostatic attraction between the nuclei of the atoms and the shared pair of electrons, which are actually oppositely charged to one another. So that's possible. Let me clarify that by giving you a simple example. In fact, I guess the example is present on the next page. Yeah, there we go. So take a look. What we are going to do is that we are going to discuss this example and we're going to count the attractive and the repulsive forces to give you a good idea how this bond exists. Now, there is an A part or A nucleus which is attracted to the electron pair, and there is B nucleus which is attracted to another. Actually, both of these are hydrogen atom, and we are talking about the possibility of forming a single bond between two hydrogen atoms by sharing a pair of electrons. Every hydrogen has one electron, and what happens is that they both share those electrons and form a shared pair in between. Let's calculate the number of attractive forces as well as the number of repulsive ones to give you an idea how this bond is so stable. Now, attractive forces. This positively charged species would attract this electron, first force. This positively charged species can attract the second electron, second force. This positively charged species can attract this electron, third force, attraction. And finally, this one can attract this electron. This is fourth force of attraction. Let's count the repulsive forces. I hope you understand that repulsive forces are between the similar charges. So this might repel this one, first repulsive force, or this might repel this one having the same charge, second repulsive force. If you add them up, you would see that you have a total of 2 repulsive forces and you have a total of 4 attractive forces. And as the attractive forces dominate, being higher in number, the bonds keep the atoms together. I hope this explains why the bond is still stable. And this is actually the diagram of this bond. Every hydrogen atom has one electron to share, and one of them is shown with a dot, the other one with a cross. And this dot and cross diagram actually explains the single bond that is formed between 2 hydrogen atoms. Make sense?
Yes.
Remember, both electrons may come from the same atom, but that's not a part of IGCSE. You will study that as a part of A levels. At this point, it has to be mutual sharing. And when I use the word mutual, I mean equal number of electrons shared from one atom to the other. If this shares 1 electron, this also has to share 1 electron. It can't be right that if this shares 2 and this shares 1. That is not going to happen in this chapter. That may happen, but not at this point. We'll study that as a part of advanced levels. Shall we move on?
Yes.
Okay, great. So, when a molecule forms from 2 atoms, the word that we use for this purpose is diatomic. The part of the name di means two, while the part of atomic tells you about number of atoms. So actually, molecules have certain fixed number of atoms. Diatomic means having 2 atoms, triatomic means 3 atoms, tetratomic means 4. We usually simply use the word polyatomic, where the word poly means many. So if it has 2 or more than 2 atoms, you can easily call it polyatomic. Well, we call the ones with 2 atoms as diatomic and any more than 2 as polyatomic. Clear enough? Okay. What is the significance of noble gas structures in covalent bonding? Again, noble gas having the configuration gives you the stability. And if you have the stability, you won't have to react anymore because you don't need to. I've already explained Octet Rule in terms of stability. That means to have 8 electrons in their outermost shell to be stable. But in this specific case, I'm going to explain another rule which we call Duplet Rule. Duplet means to having 2 electrons in their outermost shell. This is only applicable to first shell, as the first shell is so small it can only hold a total of 2 electrons. So this is only applicable to hydrogen, and nearest noble gas in this case is helium. So for hydrogen or for helium or for lithium, Duplet Rule is applied. For the rest of the periodic table, Octet Rule is good enough. All right, so only for the first 2 or 3 elements of the periodic table, as they are very small atoms, this rule is good enough for their stability. For the rest of the periodic table, the rule we're going to use is Octet Rule. Having 8 electrons in their outermost shell will give them the stability not to react anymore. All right, and having 8 electrons in their outermost shell means they have the same configuration as the nearest noble gas. We're going to use the word isoelectronic for that purpose. So when we write the formula and we write one atom in the middle and the other atoms joined to it, such as CH4, which means carbon is probably in the center and there are 4 hydrogen atoms. My bad. Just a second. 4 hydrogen atoms surrounding it. Outer atoms will virtually always have 8 electrons in their outermost shell. Only in the case of hydrogen 2, it's very difficult to think of an example where outer atoms do not have 8 electrons. However, there are some molecules where central atoms do not have 8 electrons. We are going to see a couple of those examples up next after a couple of pages. So let's move on to explain this further. Why hydrogen form molecules? Because whenever a bond is formed of whatever kind, energy is released, and that makes the thing involved more stable than they were before. When atoms release energy, they become more stable than they were before. The more bonds an atom can form, the more energy it can release, and the more stable the entire system becomes. The H2 molecule is much more stable than 2 separate hydrogen atoms. That's why hydrogen tends to form a molecule and stay in this diatomic shape naturally. And it's not just hydrogen that is going to prefer it. Let me tell you that fluorine or chlorine or bromine or iodine or even oxygen or nitrogen is going to follow the same example. Instead of existing as a single atom, which is not a stable case for them, the molecule is going to be much more stable, because when they'll form the bond, they'll release the energy and become more stable than they previously were. Remember, the general rule is the lower the energy something has, the more stable it becomes. So after releasing energy, they have lesser and less energy, and the more stable that they get. Think of it as like holding a book. If you let go of the book, it would fall to the floor. When it falls to the floor, it has lower potential energy. Therefore, it becomes more stable. So when bonds form, energy is given out. More the energy given out, more stabler would be the bond. And that's what is written over here. Make sense?
Yes.
Good, good. Let's discuss a couple of more covalent bonds. And this time, let's not go with the same kind of atoms. In hydrogen, the bond was very simple. Why? Because on both ends, there were same atoms. Let's discuss a case in which we have different atoms on both ends. For that, we're going to begin with hydrogen chloride molecule. In hydrogen chloride molecule, as you can see the diagram over here, a hydrogen shares its only electron with one of the electrons from outermost shell of chlorine. Chlorine is present in group 7, and as the group suggests, it should have 7 electrons in its outermost shell. 1, 2, 3, 4, 5, 6, and this is the 7th one. So take a look. Chlorine shares its 7th electron with the only electron of hydrogen to form a bond. This covalent bond makes the HCl for us. Take a look. The shared pair is written right in between hydrogen and chlorine like this, but you're also supposed to write the other outermost electrons of chlorine. All right, so that's how we draw it. This is a Doctrine cross model. You should be capable of drawing that model. We'll do a couple of examples, then I'm going to ask you to draw one for practice. Now, the configuration after sharing the electron of hydrogen with chlorine, the electronic configuration of chlorine is now 288. It has 8 electrons in its outermost shell. It becomes stable. Hydrogen, on the other hand, has 2. So this has the outermost shell of 2 electrons. This now has the outermost shell of 8 electrons. This is stable by Octet Rule, and this one is stable by Duplet Rule. That's why this bond is formed, because both of them gets to be stable. Remember, in IGCSE, most of the time they are going to ask you to draw the dot and cross formula with the help of outermost electrons. In that case, there is no need to draw the inner electrons. But be careful, only leave out the inner electrons if the question tells you to. There might be a question that they ask you to draw all the electrons. If they do, that means you need to draw the inner electrons. Although those kind of questions have been rare, if you take a look at 5 or last 10 years past papers, but there are a couple of examples of those too. So we need to keep our eyes open and our options open, that the examiner might ask us to draw the inner electrons as well as the outer ones. Right? Now, when we draw covalent bonds between atoms, what we do is that we use lines instead of dots and crosses. So if I move forward, you would see a structure like this. A single line represents a covalent bond when one electron was shared from both of the covalently bonded atoms, 1 electron from each one. If you have just one pair in between, a dot and cross pair like this, you draw only one line. If you get to have 2 pairs, we'll draw true lines, but that would be the case up next. Let's discuss a couple of examples with this just 1 electron shared before we move on to the next one. Next example is in line is of a chlorine molecule. Both the chlorine atoms have 7 electrons as they are a part of group 7 in their outermost shell. They only need to share a pair of electrons to have their outermost configuration of 8 electrons stable. Octet rule followed. So they only share one. And if we show these, this could be the right way to show it. Dots, 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 another dot, but shared with a cross, and the other chlorine with crosses, like this. This would be a good way to show it, right? Otherwise, if we want to show it like that, it would simply be a chlorine molecule with a straight line covalent bond with a chlorine molecule. A chlorine atom with a straight line covalent bond with a chlorine atom. Get the point?
Yes.
Great. So moving on, we can talk about the covalent bonds in different atoms, such as methane, ammonia, or water. Now, they're going to compare all 3 of these to give you an idea why do they have the number of bonds they do, and that's because of the number of valence shell electrons. Take a look. When we talk about carbon, it has 4 electrons in its outermost shell. In case of nitrogen, that is 5 electrons in its outermost shell. In case of oxygen, that is 6 electrons in its outermost shell. Remember, chlorine only shared a pair because it had 7 electrons in its outermost shell. In order to get to 8 electrons base structure, it shared 1 electron. So if a 6 electron base structure has to follow the octet rule, it needs 2 bonds. Those with 5 electrons need 3 bonds. And those with 4 electrons actually need 4 bonds in order to complete the octet rule. Do you follow me?
Yes.
Good. Then what we are going to do on the upcoming page is that we are going to discuss the number of bonds they form, and it would be pretty easy for you to understand that why this carbon is forming 4 bonds with 4 different hydrogen atoms. It had 4 electrons in its outermost shell. It shares 1 electron with each of the 4 hydrogen atoms. And that way, take a look, 1 pair, another shared pair, another one, and finally the last or the 4th shared pair. So it has a total of 8 electrons. Carbon is now balanced. While every hydrogen is balanced because of the 2 electrons it can contain in its first shell. So every hydrogen follows the Duplet Rule, while this carbon follows the Octet Rule, and they both are stabilized by 4 shared pairs in play. Hence, if you are supposed to show it like this, you can show it like this. 4 single lines with carbon in the center and hydrogen on the sides. This is what I was talking about a couple of pages back. That carbon is in the center and all 4 hydrogens surround it for a methane molecule. Make sense?
Yes.
Great. So if it makes sense with 4 electrons in their outermost shell, definitely ammonia would make sense too, because it's going to have 5 electrons in their outermost shell. Now, the one that had 4 electrons had to make 4 bonds. The one that has 5 electrons already has 5. So it's good enough for it to share just 3 electrons and make 3 bonds. Hence the formula is NH3. Take a look, first shared pair, second shared pair, third shared pair, but this one is not a shared pair. Why? Because this one is not a collection of a dot and a cross. This one is actually a collection of both crosses. And in the case of ammonia, nitrogen does not need to form the 4th bond because it already has 5 electrons, my bad. So 5 electrons plus 3 shared electrons It has now 8 electrons, hence following the octet rule, it's stable. So if carbon is stable after making 4 bonds and nitrogen is stable after making 3, you would notice that water is stable after making 2 bonds. Take a look at like over here and you'd find the same thing. However, when it comes for drawing the bond, you would see that the shape of the molecules are different than what we can simply draw. Instead of drawing all 4 hydrogen at 4 sides, we draw them a little differently so that they can easily be distant enough from each other in the similar manner so they can keep the repulsion of one bond with another, because this is also a pair of electron repelling this pair of electron, which is repelling this pair of electron, which is repelling this pair of electron. So all pairs tend to repel one another and they tend to get as far apart as possible. And this is the maximum far apart which is possible in this case. All right. So that's why this kind of structure forms in methane and this one does in water. What we use for methane is the word tetrahedral, or for water we can use other words such as triangle, pyramidal, or we may use the word triangular or bent. All right. Now the 4 pairs of electrons around the central atom in water, 2 of these pairs are electrons involved in covalent bonding. Let me go back to explain this back to you. Take a look. These 2 pairs consist of dot and cross, hence this line. And then this pair again is dot and cross, hence this line. However, these 2 are just crosses and these 2 are just crosses too. So this pair and this pair. We have different names for them. As these pairs are only consist of crosses, we call them lone pairs. However, these pairs which consist of cross and dot too, we call them shared pair. Actually, we have 2 names for them. We may call them a shared pair, we may call them a bond pair as they're involved in bonding. All right. So these pairs behave differently. Lone pairs try to repel the shared pairs a lot by this gap. That's why the structure of water is considered as bent or angular, because lone pairs try to repel the shared pairs a lot. Stuff which is explained on the next page in the first paragraph. This paragraph, you'll understand about the lone pairs and the shared pairs and how the lone pairs repel the shared pairs, and the structure of water is known as bent or V-shaped. And the molecule is slightly polar. It has a slightly negative charge on one end and positive on the other. Actually, negative end is of oxygen and the slightly positive end is both of those of hydrogen. We use a partial sign in order to explain how the charges are slight and not complete. That's why a stream of water can be bent against an electrically charged object because the water is polar itself. By using the word polar, it can be attracted by any charged species. Get the point?
Yes.
Okay. So next up would be covalent bonding in F10 molecule. This is going to be a little bit more complicated. It might take more time